I wanted to solve a couple of first-order differential equations today, and the purpose for these, in most problems in differential equations, what makes it different from, say, an algebraic problem is instead of solving for x, we're solving for an equation, y, some function such that when you plug it into its own derivative, it will satisfy this first-order differential equation. And you can also see that we're given a initial value here. So it is therefore an initial value problem where we'll actually get to solve for both the um, general as well as the particular solution towards the end. So let's begin. How do we separate variables in this differential equation? I want to essentially bring all x's and all y's to the same side, and the way that I can do that is I can get rid of dx on this side, which means I would bring it over to that side as well. And so I end up with dy is equal to xy dx. But this y, I don't want it on that side. I want to bring it over to the left with the other dy. So the way we do that, opposite of multiplication, let's divide. And so now I'm left with 1 over dy, 1 over y dy is equal to x dx. So now we have two separate equations in terms, one in terms of x, one in terms of y, and we can now integrate both sides. And the integral for 1 over y will be the natural log of absolute value of y. It has a plus c in there, so I'll note that there's a constant when we're talking about general solution for integrals. Similarly, but you'll see that it combines with the other constant later. And the derivative, sorry, integral for x is not a natural log, but rather x squared over 2. And that has its own constant after integrating. Now, the reason why these combine is these constants can be anything. They're very general. So if you were to simply combine them together to be an overall super constant c, then this simplifies our equation much better, much more. So we'll have the natural log of y, and put the constants on one side. X squared plus c, x squared over 2 plus c. Now, I still want to get my function y, so if I want to isolate y here, I can turn this all into exponential function where e is raised to these both sides of the equation. That helps us eliminate the natural log and the absolute value, as a matter of fact, since on the other side, e to any power will always be a positive outcome. So now I have, right, e to the natural log of a value. It's sort of an elimination that happens here, where we can now simply write absolute value of y or just y, because again, the other side will always be positive. And this is raised to the x squared over 2 plus c. Okay, so then, as you know, this power rule allows us to separate the two. And this is just another constant again, so really we could simplify this more to c times e to the x squared over 2. And we have a general solution. Okay, so if we wanted to stop there, box that, we found a general family of solutions. C can be any constant. But if you remember from the beginning, we did have an initial value provided to us. So let's recall this initial value that we'll plug in for x and y. Y of radical 2e is equal to 2. So y of radical 2e is equal to 2. That tells me I can rewrite this as 2 equals c e to the power of root 2e squared over 2. Simplify that down, I get 2e squared over 2. And simplify further, c e to the e squared, lots of exponents. Okay, so that tells me if I solve for c by dividing both sides by this e to the e squared. Bit of a complicated constant, but it is a constant nonetheless. See if you can keep track of all that and rewrite your general solution now into a particular solution. So what will that look like? Go back to your general solution and replace c for this 2 over e to the e squared times e to the x squared over 2. And there's your particular solution to that differential, first order differential equation.